Great. So we are going to talk through some of the enhancements and features that were developed in the ActivitySim framework since the development of the original donor model. And as a reminder, the donor model for ActivitySim is the CT-RAMP travel model, coordinated travel activity-based modeling platform. That's been used in a number of, deployed in a number of MPOs, including Southern Oregon and Portland Metro. So it's essentially a rewrite of that model system, but it's a rewrite of an earlier version that was developed for MTC and ARC about 12 years ago. And so there's been a lot of development in ActivitySim to implement the features that have been folded into newer versions of CT-RAMP, as well as extend ActivitySim beyond, in some ways, in many ways, the CT-RAMP model that was the foundation for the system. So I want to identify what those features are, and then we'll talk through a subset of them. I think we have more slides than we will be able to get through in this presentation. So if you're really interested in hearing about a specific feature, you can type it into the chat window and I'll try to make sure I get to it. If somebody can just read me at some point what people ask for, because I can't see the chat right now as I'm talking. Okay, so Joe mentioned the 2-zone and 3-zone systems. I'm going to briefly talk through the differences between them here in a minute. We've added ride-hail modes to the mode choice model. I'd like to spend a little bit of time talking through how those are treated. There is a work from home and telecommute model. Obviously, those models, though they were developed pre-COVID, are particularly of important now, given where we're at with COVID. There is a transit subsidy model and transit pass ownership model. I have some slides to talk through those. Jilin mentioned some of the enhancements that we did to better address university-related travel. That was really important for SumCog because University of Michigan transit routes represent about 1/5 of the transit ridership in the Southeast Michigan region. So David's going to talk through those. We have a vehicle type model under development right now. I don't know if I'll have time to talk through it. And the software has been enhanced with estimation mode functionality, which essentially means you can input household travel survey, synthetic population, and travel choices through the model, as opposed to a synthetic population, and get basically estimation data files out of the software. And actually estimate. There's a functionality that's been added called Larch, which is a Python-based choice model estimation package. It's based on SciPy. It's integrated into the software, so you can essentially estimate, re-estimate ActivitySim models, and it will create coefficient files that can be then used in implementation. It's very convenient for re-estimating models. We are currently wrapping up the development of a cross-border model. There was a question about whether SumCog had an explicit treatment of Canada to US travel. For SANDAG, there's a huge segment of population that travels in San Diego County but resides in Mexico. There's a special travel model that addresses that model segment that we are implementing in ActivitySim and could be used for other regions as well. Next slide. Oh, this is me. I'm controlling the deck. Okay. We're also, Joe mentioned the tranche 7 work orders that are just being executed now with the consultant team. They include these enhancements, a lot of these enhancements. A school pickup drop-off model will be implementing that. I think both the Southern Oregon and Portland Metro models already have a version of this, so that's an effort to bring ActivitySim to the same, up to the same level as CT-RAMP. Disaggregate accessibilities, which are sort of more informed, more accurate accessibilities than what's currently handled in ActivitySim or CTRAMP. Some enhancements to the shadow pricing algorithm to ensure it converges more quickly and more efficiently and better represents input data. Joe talked through the performance enhancements, and there's a number of model components that are being developed as part of the SANDAG model development that we're hoping that will eventually make their way into the ActivitySim framework as well. So moving on, I think a lot of folks are familiar with the 2-zone and 3-zone models because I've presented this at, I think, other Oregon Modeling User Group committee meetings, and most recently at the Oregon Steering Committee, the subcommittee on activity-based modeling. But just real quick, this is a plot of downtown Portland, and the transit lines are shown here. Basically in a 2-zone system, there's a subzone system called microzones, which breaks up TAZs into smaller zones. They're typically about the size of a city block or a census block. We use local streets to create them in the Portland model. They're shown here in the purple lines. And then there are aggregations of transit stops called transit access points or TAPs that one uses to build non-motorized access between the microzone and transit. And that's shown here in with the green links, all the transit stops that are connected to each transit access point. So it's it's essentially a way to get a more accurate transit path through the network, especially non-motorized paths, and use a choice model to consider all the different transit paths from an origin to a destination microzone rather than relying on transit path builders exclusively, although it still uses the transit path builder to find paths from TAPs, between TAPs. So that's now implemented in ActivitySim. The 3 different zone systems are shown here. You know, the 1-zone system is the standard TAZ-based system where all the skimming and assignment is done at his own TAZ to TAZ level. In the 2-zone system, we use TAZ to TAZ skims, but we also build all the origins and destinations are located at the microzone level, and we use an all streets network to calculate non-motorized times between microzones. And we use a rough approximation of basically time from the microzone to the closest transit stop to override the walk times in the skims. And then in the 3-zone system, we use TAZs for highway skims, but TAP pairs for transit skims. Okay, so that's the 1, 2, and 3-zone systems. The 3-zone system, by the way, does take about twice as long to run as the 1-zone system in our testing so far. So there's definitely a time trade-off there. The 2-zone system takes a little bit longer, like 15% longer to run than the 1-zone system. There's computational trade-offs, there's complexity issues, network coding issues, and so on to be aware of as you're contemplating which zone system to use. Ride-hail modes. Obviously, this is really important since you know, 2015, 2016, 2017, and emerging mobility is becoming a lot more important in a consideration in travel models. We added a ride-hailing nest to the mode choice model that considers taxi, and TNC. You can see here the skims that are used. This slide shows the distribution of wait times for taxi and TNC modes. This actually came from the City of Portland evaluation survey that was done a number of years ago. And it's essentially basing the expected wait time on the density of the origin zone, with the expectation that you know, if you live in a rural area, you're going to wait a lot longer for a taxi, but not quite as long for a TNC because of the distributed nature of a TNC ride-hail system. but it does reflect variation in the wait times that one might expect. And these can all be configured in the input file. We do represent single pay TNCs separately from shared pay TNCs in the modal options. Shared pay TNC is where you might get a cheaper fare, but you might have a longer in-vehicle time or a longer wait time because you have to reroute to pick up other passengers en route to your destination. Moving on, we developed a work from home and telecommute model. This telecommute choice model was actually estimated from Sandag data, which was pre-COVID, but it could be calibrated to post-COVID conditions. There are two aspects to this. One is the telecommute choice, which is the telecommute frequency for workers who have a regular workplace outside their home. And the purpose of that is to represent the effects of a telecommute program on model outcomes and test the implications of changes in telecommute program availability and participation, while accounting for the likelihood of different workers participating in such programs, and also to test COVID and post-COVID scenarios. The telecommute model only applies to workers with a regular workplace outside home. Unfortunately, the previous version of ActivitySim didn't consider workers who work from home explicitly, so we added that largely as a tool so that we could also model telecommute choice reasonably well. So workers who work from home is also becoming an increasing phenomenon, the remote workforce, as employers might close offices or hire workers who work much further from a regular commuting distance. So we might also expect that percentage to increase over time. And it's another knob to turn in the model. This shows some percentages from the Sandag Household Travel Survey data, which was collected in 2017, I think, on telecommute frequency that was used for model estimation. This is the telecommute frequency model. The alternatives are never or less than 1 day per week. Those alternatives were all grouped into one because we did not observe noticeable differences in commuting behavior or travel behavior for people who commute less frequently than at least 1 day per week. So then for telecommuters, the alternatives are 1 day a week, 2 to 3 days a week, or 4 more days a week. And you can see the explanatory variables here: occupation, income, distance to work, whether the person has paid parking or not, whether they're a full or part-time worker, presence of children in the household, number of cars, and so on. And then the effects of that model are incorporated into downstream models. So workers who telecommute regularly are less likely to go to work on any given day, and it goes without saying. They're more likely to either stay at home on the entire day or engage in some non-mandatory travel. Now, note that was pre-COVID travel conditions. We really need to re-baseline these effects post-COVID, because I suspect that the telecommuting workers are actually less likely to travel than pre-COVID. But for folks who do travel and who don't go to work but do travel, they're a lot less likely to make a lot of complex travel. So they're more likely to make just one non-mandatory tour or a non-mandatory tour with less intermediate stops. We did test for other effects on other model components and didn't see any significant differences. How am I doing on time?
You have 4 minutes.
Okay, then I'm going to give Dave a chance to talk through the university enhancements. David?
Thanks, Joel. As Joel said, and Jalen mentioned, University of Michigan Transit accounts for roughly a quarter or a fifth of the entire transit in the SEMCOG region. So getting this was very important. And when we first stood up the phase 1 model, we saw that we were missing roughly 80% of the ridership. There's a couple reasons for this. Kind of the first reason is that we weren't allowing students to travel across from campus to campus. So the University of Michigan is kind of separated into a north campus and a south campus, as you can kind of see here on this map. And what was happening is that if your dorm was near the north part of campus, you were just going to school at the closest zone there with enrollment, and same kind of on the bottom. So the school location choice model was often just selecting the closest zone and just not modeling or not accounting for this intra-campus travel between the north and south regions. And the other big problem that we noticed was that we weren't including people parking at the university and taking transit. So there's a bunch of parking lots kind of on the north part of the campus that have transit routes that run from the parking lot down into the more densely populated southern campus. And so we were missing those routes as well. Next slide, please. Joel, are you?
Oh, sorry. Yeah, let me do that for you.
So we essentially put in a couple of enhancements to address these two problems. The first was allowing students attending a quote unquote major university to follow a more realistic daily pattern. So we increased the number of university stops on university tours, right, to kind of model people that might go to a class and then go to lunch and then go to another class. That's more often seen at kind of these big universities and not so much the commuting schools. And then the other, the other thing that we did was change the tour and trip destinations, and we randomly sampled it from that university's enrollment. So what this did was allow people that lived in the North Campus to have classes that were in the southern part of the campus and vice versa. The other thing we did to address the parking issue was we forced people that were driving to a campus zone and forced them to choose a parking lot, which we sampled based on lot size. And then we treated those subsequent trips when they're parked as being walk transit tours, so that when they're choosing their trip mode on their tour, they don't have any access to driving alone, which forced them, a lot of them, to take the transit. So what happened? Well, we saw the University of Michigan ridership much more closely matched the data after putting these enhancements in. So this was a good example of a very region-specific problem that we were able to address based on ActivitySim's kind of modular development, and able to kind of insert, extra extensions where we kind of found them necessary in this particular region. And then I guess, yeah, thanks, Joe.
Okay. Are we at time, or how are we doing, Liming?
Yeah, we are at 20 minute mark. So yeah, 10, 11, 20. So unless you want to talk maybe quickly, a couple of minutes for any to essentially wrap up, or however, whichever points you want to highlight.
I would just, my concluding remark would just be that it's really nice to be able to work on a project where the platform is being enhanced in multiple ways to address multiple clients' needs, and there's a real spirit of sharing across all the agencies and the consultant team in terms of contributing to a common framework. And in case anyone hasn't said it yet, if anyone in this meeting is considering developing an activity-based model, I hope they would consider ActivitySim and contributing back to the framework, so the broader planning community can benefit from those enhancements.
Great. Okay, questions for Joe and David? I do have one to begin with, as others come up with their questions. When you talk about the 2 and 3 zone systems, maybe I missed, but what is the distinction between a TAZ and MAZ besides the size of the MAZ?
They're essentially subsets of zones, so they're disaggregations of TZs.
So essentially subdivide a TAZ into smaller.
Yeah, and typically we'll use like the local street network to do that, to try to get it, like logical travel sheds, I guess. And of course, all the land use data needs to be specified at the MAZ level rather than the TZ level in the implementation, which is another requirement for running the model.
Right. So in the case when the reason that a user may want to keep their TAZ instead of just use the MAZ to replace their TAZ is primarily for performance or for data availability?
Yeah, we use TAZs for auto skimming and assignment. Of course, the implications of zone size are a lot less significant when you're talking about travel times in cars versus travel times by foot.
Right.
So, it's a trade-off between computational performance and accuracy.
Mm-hmm.
But you can imagine with some models have like 60,000 microzones. Mm. So creating a microzone to microzone skim for all microzone pairs is quite onerous.
Right. Okay, that's helpful. Right. Okay.
There was a question from Supin too about the density of the links used to connect transit access points to transit stops. Mm-hmm. I think since the development of the metro model, we're now using k-means clustering to generate the transit stop coverage. And what we're finding is that using the k-means clustering algorithm, we're able to get the taps much closer to the transit stops on average than the algorithm that we were using previously for metro. But yeah, basically for metro, the algorithm was finding the closest stop, generating a tap for it, and then going out to each next closest stop according to a max distance threshold. K-means clustering tends to find tap locations that are more evenly distributed, I guess. I hope that answers your question.
Okay, I see no more questions.